This is part 2 of a series of introductory astrobiology videos that I'm working on. So these are ones meant to introduce you to the field of astrobiology. Now, in part 1, or in the first part, we took a look at our own cosmic neighborhood. We learned some basic facts about astronomy, things like, our own solar system and galaxies and some terms. But now in this part, we're going to focus on how we got here. Because now that we've sort of understood, or at least gone through a lot of the basics of astronomy, now we can start delving a little bit deeper into some of these interesting questions from astrobiology. This whole idea of how we're going to find alien life or life on other planets. So our main goal for this series of videos here for part 2 is going to be to try to answer this question, how did we get here? And that's going to include 4 steps. So the first step is going to be all about the building blocks of life. So there we're going to talk about what are we actually made of. Then next we're going to talk about how those building blocks were made. And after that we'll talk about how we define life. And finally, how life might have actually started on Earth. So let's get going right away. What are we made of? Well, we're mainly made of these elements. Now, if you're not sure what an element is, that's maybe something worth looking up. But these are elements. Those are basic building blocks of a lot of materials. In fact, most materials you think of are made of elements. It used to be thought that those were the smallest building blocks, but it turns out those can be broken up into pieces like protons and neutrons and electrons, and those are even broken up further into quarks and other really weird, funny things. But we're doing an introductory version, so we're just going to call everything elements. And there are lots of different elements. I mean, there is the periodic table of elements, so that tells you all the different symbols there are. Now, these are organized according to a lot of similar features that they have, but they go like this. 1 is the first one, it's called hydrogen, and then 2 is helium, then 3 is lithium, beryllium, boron, carbon, nitrogen, oxygen, and so on and so on. We're mainly going to be concerned with some of these basic elements here, in fact, some of the most commonly occurring ones. So when we talk about here what we're made of, we're mainly made of hydrogen, carbon, nitrogen, and oxygen. Seems a little bit weird to think of that, right? That your own body is mainly made up of these 4 elements. I'd like to think that I'm made up of a lot more interesting things, but it turns out you're mostly these. Of course, you've got a few other elements, of course, but this is the vast majority of what makes up you, is different combinations of hydrogen, carbon, nitrogen, and oxygen. And I'm going to be elaborating on each of these 3 here in the next slide. So the first thing is the fact that we're mainly made of these 4 elements. The next thing we're going to talk about is how we're mainly carbon-based. And finally, the most interesting, I think, and profound, is that we're made of star stuff. So first of all, with the hydrogen, carbon, nitrogen, and oxygen, maybe let's try to circle those. So there's hydrogen. That's the first one. We're also made of carbon, and nitrogen, and oxygen. Those are the main elements that make up a human. In fact, that make up almost all living things. I think it's pretty interesting that we are made up of 4, these 4 right here, of the 5 most abundant elements in the universe. So you might wonder, well, what about helium? Because helium, it turns out, is the other. I mean, these are the 5 most abundant elements, and yet we're not really made up of much of helium. Now, I mean, helium itself, it doesn't really work very well. It doesn't like to bond. It doesn't like to sort of play with others. That's because it's a noble gas. Those are the ones in this column right here. And that means that it's perfectly happy on its own. It doesn't really need to bond with other elements. So these elements, what they are, they're the basic building blocks. Okay, those are the things that sort of make up us. So that was the first one, that we're mainly made up of hydrogen, carbon, nitrogen, and oxygen. Those in different combinations make up a human. And now we say that we're carbon-based. This is a funny t-shirt here, but we're mainly carbon-based. Now, what do we mean by that? Well, carbon is the key component. Okay, so this is the key thing here, is that carbon is a key component. In other words, it's a very, very important piece for all life on Earth. So key component for life. At least this is on Earth. Now keep in mind, We only know our things about life are only based on what we've seen on Earth, because we don't have any other data points. We'd like to have lots of research done on different forms of life on other different planets, then we can have a lot better statistics. But here's the problem. We only have one place we know where there's life. It's here. So all we can do is use our best guesses based on what we see here. And what we have tried to do, though, is take a look at what other forms of life are there on Earth. Not just humans, but plants, bacteria, anything that's alive. And it turns out carbon is a key component of life. Almost everything has carbon in it. Now, the elements of carbon, those like to bond with other elements, and those make molecules. And those end up making all of life. So maybe we can write that down. So we have carbon, and that ends up making what we call molecules. That's just when you combine carbon with other things like what I just showed you here, like hydrogen, nitrogen, and oxygen. So that's why we say we're carbon-based, because carbon seems to be very, very important. It's always there. So carbon, that ends up making the molecules, and those molecules, of course, make up life. Those are the molecules that we find in life. So it seems to be very important. Now, some have actually suggested silicon-based life. This is something maybe like this. So silicon-based, because we say we're carbon-based life. So here's a question. I've heard some people talk about silicon-based life. Now, the reason why people talk about that is because in this periodic table here, we can see that carbon, turns out it's got something very special. It's the fourth column over, 1, 2, 3, 4. That tells you something about how it likes to bond, and it turns out, it goes like this, and it's got little places where other elements can actually bond with it. These are called valence bonds, and there's a whole field of chemistry that's involved in this. But we're just doing an introduction, so it suffices to just say that it's like this. Well, just below it, silicon also has this. So in other words, silicon would also go like this, with these little bonds like this, these 4 different things that want to sort of bond with other elements. But it turns, so a lot of people have said, oh, maybe there could be silicon-based life. But I wanted to actually try to talk a little bit about that. Silicon-based life, I suppose it could be. It's similar place in their periodic table, 4 bonds. But carbon allows more flexible bonds. And that's really important. So what we could say then is that, the silicon would be more rigid. So in astrobiology, we don't think that there's silicon-based life. But what's really important, though, is that we think we need to look for carbon-based life. So this is the main thing right here, is that carbon, it likes to form these molecules like with H and, not C, H, N, and O. So it likes to form, with these hydrogen, nitrogen, and oxygen. They like to make these nice complex chains. That makes up life. We don't think that there's silicon-based life. It doesn't seem to make sense, and we've never seen it before. So what we do is we're going to be looking for, so when we're looking for aliens on other planets, we're going to look for carbon-based life. Of course, we're going to keep our eyes open for other forms, but so far we think there could only be carbon-based life. So I think that's actually pretty interesting. Last but not least is this notion that we think we're made of star stuff. Now, I really like this, that we are star stuff. We are the universe made manifest, trying to figure itself out. This is a neat little necklace here that you can buy, I guess. But this term, star stuff, that actually came from a guy, an astronomer named Carl Sagan. So again, he was actually quite influential. He was not only a very good astronomer, but very good at explaining things. He did it much, much better than I could. But he was very, very good at explaining things. So he was talking about how life is, or how everything we are, is made of star stuff. Now, what do we mean by that? We mean that, we really think that all the elements that make up our own bodies. Remember, I was talking about these elements, how these elements make up us here. We're made of these elements. And it turns out these elements that make up us, we think that they were all made in stars, which is, I think, so cool and so ridiculous sounding. So we're actually going to go into more detail with that. So what I'd like to do now is just go over a little bit about how were those elements made. Because if we have all these elements that make up humans and everything that's alive, there's hydrogen, carbon, nitrogen, and oxygen, plus all the other stuff, it all had to be made somehow. So we actually have a really good theory for how this works. And in fact, it's been checked in a lot of different ways. We don't know for sure what happened, but it seems highly likely that this is the case, which I think is so cool. So how were the elements made? Well, in order to make all these elements, step one, you need a Big Bang. Now this Big Bang, it ends up making a universe. So it turns out, through some very, very strong evidence, it turns out when you look at different galaxies around us, all the galaxies are going away from us. So that explains a little bit that the universe seems to be expanding. And if it's expanding, it makes sense to think of what happened before. Well, then things were closer together. So that's why they've sort of coined this term Big Bang. So that ends up making a universe. Now, when we talk about this Big Bang Theory, I mean, not only is it a good TV show, I don't know if you've ever seen that show, but I highly recommend it. It's funny and silly and weird. But no, I'm talking about the real thing. So not just the TV show, but the actual theory. And the theory goes that at some time, around 13.7 billion years ago, for some reason, the universe, everything seemed to be in one place. So everything sort of started off all in one point. And eventually then, for some reason, which we have no idea why, everything started expanding. And when it expanded, it was a big, giant explosion. But the key thing is this, that the Big Bang in the universe, it ended up making, so I'll say made, the hydrogen. So we think that this element H, hydrogen, was mainly made in the Big Bang. So when the universe was first made, we think that it made the hydrogen, and actually a little bit of helium as well. But those are the sort of current theories. Now what happens after that? Well, now you have a bunch of hydrogen. So what happens with the hydrogen? Well, we talked about this before, but what happens with a star? Let's say you have a few different hydrogen atoms, and they can actually sort of, through gravity, they might actually want to attract each other. They might want to sort of join up with each other, so they might go towards. What happens then when it gets hot enough, you have what we call nuclear fusion. And that's when you're converting hydrogen to helium. Remember, we learned before, plus energy. So whenever you're doing this, you also get energy, which is in the form of light. And that's great. That's what makes stars bright. So in the center of the star, it would be what we call burning or converting hydrogen to helium. And it turns out that when it's done with that, see what happens in a star, there's this constant battle. What's happening is inside the star, this is the star right here, in the center of it, we have gravity, which is acting inwards, because that is actually a force. Everything that has mass attracts everything with mass. So this star is going to feel an inwards force, sort of all the matter wants to go into the center. But it turns out there's an equal and opposite force, and that's caused by the radiation pressure. In other words, the pressure from this extra energy, this extra light. So we call this right here, right now it's what's called hydrostatic equilibrium. It's when, all these different forces that are fighting each other, so the inward gravitational and the outward sort of from the light, we call that radiation pressure, they're fighting against each other and they're equal. Nobody's winning. So that is when we have a stable star. That's, for example, when it's converting hydrogen to helium. But what happens when it runs out of hydrogen in the core? Well, when it runs out of hydrogen, it can't do this reaction, so there's less energy. That means there's less outwards push. Well, what happens with gravity? Then it wins, so gravity squishes everything. Now, of course, when it gets squished, guess what? It gets hot enough in order to convert helium into heavier elements. And this process continues on and on and on. Each time it does that, there's successive rings, basically. So what happens is this, you end up in a very, very old and very mature star. You're going to have hydrogen burning to helium. You're going to have helium burning to other things. And you'll have carbon that was burning to things, and neon, and oxygen, and silicon, all the way up to what we call iron. It turns out the element iron is the most that a star can actually burn. In other words, it can do fusion of iron, but no higher. In fact, this is the stopping point. So then the next thing is, what happens then? What happens when it can't make heavier than iron? Well, remember what happens. It can't push outwards anymore, so that means everything collapses. So this entire star, basically everything is going to end up coming inwards. We actually say it goes in free fall. It's actually going to go really, really fast. Now what happens with iron, something very special happens here, that this material can't be squished anymore, so we call it an electron degeneracy pressure and also neutron degeneracy pressure. Those are advanced terms, so basically what happens is the core of the star essentially goes really solid, and that means all the other material then can't really go inwards anymore, so what does it do? It bounces off. And when it bounces off, it makes what we call a supernova.